Hello my dear students. So in my last class we understood about electrochemical series. What are the applications of electrochemical series? Like to calculate EMF of a cell we use electrochemical series, and to determine the feasibility of a reaction we use electrochemical series. So what exactly is an electrochemical series? So it is a series of electrode systems obtained by arranging them in the increasing order of reduction potential is called as electrochemical series. So it is a table, it is a series of electrode systems. So that is used, that electrochemical series is used to determine the free energy change and equilibrium constant of a cell reaction. Further, so these electrochemical cell or series is also used for the prediction of displacement reaction. And later we understood about the measurement of EMF of a cell. So there we saw the circuit, how the connections are made, and with the help of that, so how we are going to measure the EMF of a cell was understood, and at last types of electrodes were seen. So that is a primary electrode and secondary electrodes were seen in my last presentation. So in this session, so let us understand how the construction and working of hydrogen electrode is done. So what exactly is this standard hydrogen electrode? So this is used as a reference electrode when calculating the standard electrode potential of a half cell. The standard hydrogen electrode is often abbreviated as SHE, and it is standard electrode potential is declared to be 0 at a temperature of 298 Kelvin. This is because it acts as a reference for comparison with any other electrode. So platinum is used in the standard hydrogen electrode due to the reasons like platinum is a relatively inert metal which does not corrode easily. Platinum has catalytic qualities which promotes the proton reduction reaction. The surface of platinum can be covered with platinum black, a fine powder of platinum. So this type of platinum electrode is called as a platinized platinum electrode. And platinum also improves the reaction kinetics by absorbing hydrogen at the interface. So these are the use of platinum in the standard hydrogen electrode. So now let us understand how do we construct this standard hydrogen electrode. A rectangular platinum plate coated with platinum black is welded to platinum wire. So this is the platinum wire or platinum foil. So observe in this figure, the wire in turn is fused to glass tube. So it has been fused to the glass tube, and this tube is fused to jacket tube having a bell shape at the bottom. So this is having a bell shape at the bottom. There is a side tube at the top and it acts as a hydrogen inlet. So this is the hydrogen inlet. So the hydrogen gas at 1 atmospheric pressure is going to be passed through this inlet. Two holes provided on the bell part of the jacket which acts as the hydrogen gas outlet. Okay, so from there, so the hydrogen gas is going to be liberated or separated out. The parts that make up a standard hydrogen electrode are mainly a platinum electrode which is covered in finely powdered platinum black, that is platinized platinum electrode, and a hydrogen blow, a solution of acid having a H plus molarity of 1 mole per cubic decimeter. And the standard hydrogen electrode also contains a hydroxyl which is used to prevent the interface of oxygen. The other half cell of the entire galvanic cell must be attached to the standard hydrogen electrode through a reservoir in order to create an ionically conductive path. So this can be done through a direct connection through a narrow tube or even though the use of a salt bridge. So this is the diagram of standard hydrogen electrode. Now let us understand the working principle of this standard hydrogen electrode. A little of mercury is added into the glass tube and wire is dipped to achieve electrical contact. When the electrode is to be used as a standard electrode, it is dipped into HCl. If the electrode is standard electrode, then 1 molar HCl is used. Hydrogen gas is passed from the top inlet. So as I shown in this diagram, so this is the hydrogen gas inlet. So here we are going to pass the hydrogen gas. The pressure inside the jacket increases. So when hydrogen gas has been passed through this inlet, so the pressure is going to increase inside the jacket. The acid level inside the electrode is pushed down and the platinum plate is exposed to hydrogen gas, and as a result hydrogen is absorbed by platinum. When the liquid level further falls, gas escapes and the pressure falls. Liquid level rises. Now the adsorbed film of hydrogen is in contact with hydrogen ions of the solution. Hence, at this stage we can observe a equilibrium. A equilibrium is established and the potential developed at equilibrium is picked up by platinum. When this electrode functions as a reduction electrode, then the equilibrium reaction taking place will be represented in this way. So that is H plus E minus, which is a reversible reaction and it is a equilibrium reaction. So that is why it will give rise to half H2 molecule. The reduction potential developed can be expressed as EH, which is equals to EH naught plus 0.05915 log to the concentration of H plus. Concentration of gas in the reduced form, it takes as unity if the gas is passed under 1 atmospheric pressure. So therefore the concentration of H2 is equals to 1. So hence EH is equals to EH naught plus 0.05915 to the log H plus divided by H2 to the concentration or to the power of. So this is how the working principle of standard hydrogen electrode is described. So next is a standard hydrogen electrode. How we are going to define a standard hydrogen electrode? A standard hydrogen electrode is defined as a hydrogen electrode constructed by dipping into a solution of hydrogen ions of unit concentration under a partial pressure of 101.3 kilopascal. The potential of hydrogen electrode is taken as 0. Hence, EH naught is equals to 0. So this is a standard potential. So EH naught is called as a standard hydrogen electrode potential. So the potential of the electrode is given by the expression EH is equals to 0.05915 log to the concentration of H plus. So on taking negative signs on both the sides, so minus 0.05915 into minus log to the concentration of H plus, and on simplification, so it gives the value of minus 0.05915 pH. So the standard reduction electrode can be represented as H plus, which will be in the concentration of 1 molar, and platinum, so which is constructed with the help of half of a molecule of H2, that is at 1 atmospheric pressure. Next is what are the limitations or disadvantages of the hydrogen electrode? The construction and working of the electrode is difficult due to the following reasons. Equilibrium is attained very slowly. Hence, hydrogen gas has to be passed for a longer time. Hydrogen gas should be extremely pure, otherwise platinum gets poisoned. Hydrogen electrode cannot be used with solutions containing oxidizing agents. Since hydrogen is a reducing agent, definitely the hydrogen electrode cannot be used with the solutions which contains oxidizing agents. And it is difficult to adjust and maintain a constant pressure. This electrode is used as a primary standard, that is, standard hydrogen electrode is used as a primary standard, and the potentials of other electrodes are standardized using a standard hydrogen electrode. Hence, other electrodes are known as secondary electrodes or reference electrodes. What is meant by a reference electrode? So it is not possible to directly measure the potential of a single electrode. In all measurements, a set of two electrodes are to be combined using a salt bridge to form a cell. The EMF of the cell is determined potentiometrically. So we all know that the EMF of the cell is given by E cell is equals to EMF of the electrode of right hand side minus EMF of left hand side electrode. Knowing the EMF of the cell and the potential of one of the electrodes, the potential of the other can be calculated. The electrode of known potential used above is called as a reference electrode. So the electrode whose electrode potential is known, already known, so that is called as a reference electrode. We are using it as a reference to calculate the electrode potential of the unknown electrode. One such reference electrode is called as calomel electrode. We all have heard about calomel electrode. Potential of this electrode is first determined using standard, that is a primary electrode, which is called as a standard hydrogen electrode. So now let us understand what is meant by a calomel electrode and how do we construct this calomel electrode. The electrode vessel consists of a bulb. So this is a bulb. If you observe in this picture or a diagram, so you can see a bulb in which a little of mercury, that is Hg, is placed at the bottom. So here at the bottom, so mercury has been placed. Above this layer, a paste prepared by grinding calomel with a few drops of mercury and some KCl solution, that is potassium chloride solution, is placed. Okay, so this is potassium chloride solution. The whole vessel is then filled with saturated KCl. All this is KCl solution, saturated KCl solution, and sealed off. The tip of the side tube is always placed under saturated KCl contained in a beaker. The electrode is represented as Hg2Cl2, which will be in solid state, and KCl solution. So this is how the electrode is represented. Hg2Cl2. So one line KCl solution. The electrode is represented in this way. It has a reduction potential of 0.243 volts at 25 degrees centigrade. The potential of calomel electrode depends upon the concentration of KCl solution. So how, in what concentration we are going to use the KCl solution, so that indicates the potential of the calomel electrode. Say for example, if we use 0.1 normal to 1 normal and standard solution of KCl have been employed, so then the calomel electrode will have more electrode potential. The electrode with the 0.1 normal KCl is preferred for accurate work as it has the lowest temperature coefficient. The electrode is reversible. Okay, so if the electrode reaction involves reduction, then the Hg2 plus ions furnished by the sparingly soluble mercury chloride would be discharged at the electrode. Hence, more and more calomel would pass into the solution. So this results in an increase in the concentration of chloride ions. The electrode reaction as a reduction electrode may be represented as HgCl2 plus 2E, which gives rise to 2Hg plus 2Cl chloride ions. The electrode is therefore reversible with respect to chloride ions. So next is about metal insoluble salt electrode, that is a silver chloride electrode. So how we are going to construct a silver chloride electrode? So this is the diagram which represents a silver chloride electrode. So to construct this, a clean silver rod and a platinum wire are dipped into silver nitrate solution, making silver rod as the cathode and platinum wire as the anode. Current is passed through the solution. As a result, a fine crystalline layer of silver is deposited on the silver rod. Next, the rod is dipped into one normal HCl solution. It is then made the anode and current is passed. Chlorine liberated at the anode converts a part of silver into silver chloride. The color of the rod changes when it becomes purple. Flow of current is stopped and the electrode is removed, washed with water and preserved under water. The resulting electrode is called as silver chloride electrode. So this is an electrode reversible with chloride ions. When the electrode acts as the reduction electrode, so the following reaction is going to take place. That is, so when AgCl is going to form a silver and chloride ions. So the reduction of the electrode is represented in this way. So the electrode is reversible, as I said, with respect to chloride ions, and the Nernst equation for the silver chloride electrode is given by, so EMF of the electrode is equals to E naught, that is the standard reduction potential of the electrode, that is silver chloride electrode, plus 2.303 RT divided by NF to the log concentration of AgCl divided by the concentration of Ag and Cl minus ions. Or it can also be simplified and shown or written as E electrode is equals to E naught electrode minus 2.303 R divided by F into log Cl minus. So next is the measurement of single electrode potential using calomel electrode. As an example, let us consider the determination of reduction potential of zinc electrode using calomel electrode as the reference electrode. So here I have used calomel electrode as the reference electrode, and I am going to measure the electrode potential of zinc electrode by using a calomel electrode. First, zinc electrode is connected to a saturated calomel electrode using a salt bridge to form a cell. As we all know that we can write or represent the cell in this way: Zn bar Zn plus 2, and this is the salt bridge. So the double line what I am showing here, so this is the salt bridge, and it is connected to a saturated calomel electrode. The EMF of the cell is given by E cell is equals to E calomel minus E zinc electrode, that is E reduction potential of calomel electrode minus reduction potential of zinc electrode. When E calomel and E zinc are reduction potentials of the calomel and zinc electrodes respectively, the EMF of the cell is experimentally measured using a potentiometer. The reduction potential of a saturated calomel electrode is 0.243 volts. So by using this value, so E electrode potential of zinc is equals to 0.243 minus E cell, and by knowing E cell, that is EMF of a cell, that is E cell potential of a zinc electrode, can be calculated. And to determine pH of a solution using hydrogen electrode, what we are going to do is, a hydrogen electrode is set up by dipping into a solution containing hydrogen ions. So this experimental electrode is connected to a standard calomel electrode to form a cell, and that cell is represented as PT half H2H plus, which is connected through a salt bridge with a calomel electrode. And the EMF of the cell is calculated by using this expression, that is EMF of a cell is equals to EMF of calomel electrode minus EMF of hydrogen electrode. And we know that EMF of a cell is equals to, so this is standard hydrogen electrodes EMF, so that is already been reported, so that is minus 0.05915 pH. So this just now we have studied in standard hydrogen electrode. So substitute this value, and by knowing this E cell value and the EMF of the calomel electrode value, by rearranging this equation, we can determine pH of a solution using this hydrogen electrode. That is, if we take pH towards the left hand side, so EMF of a cell minus EMF of a calomel electrode divided by 0.05915 gives us the pH of a solution. So this is how we can use this standard hydrogen electrode to find out the various different EMF or reduction potential of unknown electrodes. So I am going to stop it here, and in my next class we will see or will understand what is meant by oxidation reduction electrode. So the examples of oxidation reduction electrodes are quinhydrone electrode. Okay, so we are going to study about quinhydrone electrode. So how this quinhydrone electrode is constructed, and it is an oxidation reduction electrode. Okay, so here we are going to use an organic compound to construct an electrode, so which will determine or which helps us to find out the EMF of a particular electrode or a cell. So let us meet in my next class. Thank you, dear students.